Okay, so 4.3, we're going to talk about the chain rule, which has to do with composite functions. So this first part's a little reminder about composite functions. So this first one, there are two ways to kind of do this. You can plug in g of x first, or you can write f with g of x in it. I'll show you. Okay, so the first one, I'll do one way. So I'm going to say that's f of x over 5 plus 7. So I'm substituting for g of x right here. And then whatever's in this parentheses, you go negative 6 times the thing in the parentheses plus 9. So the thing in the parentheses was x over 5 plus 7. So we get negative 6 over 5x minus 42 plus 9. Okay, for this one I'll do it the other way. So g of f of x is f of x over 5 plus 7, because whatever's in the parentheses goes where x was. And now I'll plug in for f of x, negative 6x plus 9 over 5 plus 7 equals negative 6/5 x plus 9/5 plus 35/5. So again, this 44/5 is, I've got 9/5, and 7 is 35/5. So 35/5. Okay, so now I'm going to do the opposite thing. You can see multiple things are happening, and we now want to write it as a composite function. So for the first one, the outer function is, it's sort of like a PEMDAS order, so I can see this power, so parentheses and exponents basically at the same time. That's the outer function. So I'm going to write down that rooting is a thing that's happening. But before I can root it, I need to plug it into 3x squared minus 1. So that's the inner function, the thing I plug it into first before I do the outer function. So that means h of x is square root of, that's the f part, 3x squared plus minus 1. So that's f of g of x. So the thing you do first is in here, the thing you do second's out here. And then, and it doesn't matter what you name them. You can name them anything you want. So I'll name the outer function g this time just for kicks. This one, the very dead last thing you do is take it to the 7th. If I gave you 4 to plug in, you'd plug it in here first, and then you'd add 8, and then the last thing you do would be to go to the 7th. So I'm going to say taking someone to the 7th is one of the functions, and the other thing that happens is the 5x squared plus 8. And you could write this as the composite of 4 functions. You could do x squared first, then do times 5, then do plus 8, then do to the 7th, and kind of write those all in reverse order. But we don't need to, because we can easily differentiate these two, which is the goal. As soon as you get something you can differentiate easily, that's fine. So h of x is, f of x is the inner, that's what happens first, so g of x is the outer, because that's what happens last. Now, right here, what the intention is, kind of what I mentioned in a previous video about how things end up appearing twice. Okay? So let's look at this. I'll just do it using the product rule first. Sorry, skipping steps, I'm thinking ahead here. So u prime equals 2 times 3 is 6. Drop 1x. V prime, same thing. So u prime v plus v prime u is 6x times 3x squared plus 4 plus 6x times 3x squared plus 4 equals, I'm going to say 2 times 6x times 3x squared plus 4. And the argument I want to make is that this 2 is because of that 2 right there, because these appeared 2 times. So I end up with 2, and each time I've got the derivative of that function times that function, because both elements in play here are the same. So another way to think about it is you take a derivative with respect to this whole thing. So I have someone squared, so I bring the 2 down and have that thing to 1 fewer, but then I multiply by the derivative of the inside. So this is, for the M&M analogy, first you melt the candy by doing the 2, this thing, to the 1 fewer than 2, and then you melt the chocolate with the 6x. I want to show you very quickly, suppose that you had y equal to u times v times z, where they're all functions. So I'm going to talk about the product rule now. So I'll first treat this one as its own thing. So now I would have u prime vz plus u times, now I need the derivative of this, but this is also a product. So inside I have v prime z plus vz prime. So I've applied the product rule 2 times. So I have u prime vz plus uv prime z plus uvz prime. So note that I had 3, before when I had 2 functions, I had 2 things added up, one derivative, one not. This time I have 3 things added up because one of them has u prime, one of them has v prime, one of them has z prime. So this is actually forever. If you had 5 things, you just take the derivative of the first one times the other 2 plus the derivative of the second one times the other 4. The derivative of the second one times the other 4 plus the derivative of the third one times the other 4, and so forth. So if these are all the same, so if I had y equals x plus 7, let's say 2x plus 7 square, fifth, to the fifth, then the first one I'd have the derivative of the first 2x plus 7 times all the other ones. And on the second one, I'd have 2x plus 7 times 2 times 2x plus 7 cubed. So I'd have the same thing. So in each case, I get the function 1 fewer times, and I get the derivative. So the rule is, if y is another function, let me say f of x, to a power, then y prime is bring the power down, f of x to the n minus 1 times the derivative of x. It's that 1 in the product that's getting its derivative taken every time. Okay, and generally speaking, so that this is the one I just said. But generally speaking, if you have a derivative, you're taking a derivative with respect to x, but your function is really a function of another function, then this is why it's called the chain rule. You can line these up as long as they'll cancel. They're not actually canceling, but they always do. So it won't mess you up if you think about it that way. So dy dx is dy du times du dx. So if I can easily write it as y is a function of u and u is a function of x, then I can use this version of this rule. Okay, so on the first one, I first differentiate the outside function, which is the 5 something to the 1 fewer than 5. Then I differentiate the something. So this is the candy part. And I copy that down. And then I take the derivative of the chocolate. Like that. So I'd probably go ahead and change that this way. And then the other way to think about it, if you want, is in this case, f of x is minus 2 times somebody to the negative 3. So the somebody's always the chocolate. So you let u be the chocolate, and then you rewrite this in terms of u. So then I'll call this y. So dy du is now easy, because this is just a little monomial. So negative 3 times negative 2 is 6. U to the minus 3 minus 1 is minus 4. So when I say it's easy, I don't mean it's easy necessarily to do it how I just did it, but if you write each of the steps in, this is a monomial. So it's the way we've been doing things at any rate. And then du dx is 4 line. So dy du, du dx, which is then dy dx is 6u to the negative 4 times 4 is 24, and now I have to put whatever u was back in. And then that's done. So whichever way makes more sense to you, just do it that way. Okay, so f of x is that to the 1/2. So f prime x, bring down the 1/2, parentheses, 1/2 minus 1, times derivative of the inside. 3 times 4 is 12, x drop 1 degree, plus 5. So let's see, I'm going to rewrite this as a fraction. That's on top, 2's on bottom, and this is on bottom. And then this one is a product. So I have, and if you like the u substitution way, try doing that for that one. Just stop this now and try doing that and see if you can do it okay. This one, u is already going to be busy in the product rule, so I'm going to not use the u substitution here. It's very confusing. So u is z, v is 6z plus 1 to the 4/3. U prime is 1. V prime is, bring down the 4/3. Leave the chocolate alone because we haven't gotten to it yet. 4/3 minus 1 is 1/3. And now we're to the chocolate, so now we have to differentiate the chocolate. 4/3 times 6 is 8. Okay, so u prime v plus v prime u is 1 times 6z plus 1 to the 4/3 plus v prime 8, 6z plus 1 to the 1/3 times z. Now I'm going to factor out the lowest power of 6z plus 1, just like you would if you had a bunch of x's, you'd factor out the lowest power. The lowest power is 6z plus 1 to the 1/3. I have 4/3 here. If I take 1/3 out, then I've still got 3/3. So that's just 6z plus 1 now to the 1. So it's just this. And then plus 8z, and that part I've taken completely out. And now that one's done. Okay, now this is equal to x squared plus 2 to the negative 10. So if I was doing a u substitution, u is always the chocolate, so u is the thing you do first if you were plugging in, but last in this pattern. I'm kind of undoing the thing, so x squared plus 2, so h prime, I'm going to call that y, sorry, I'm going to call this y, so this is y prime. Let me just, okay, forget this, because I was using this. dy dx equals dy du du dx. And dy du is, you know what? I don't think that I went off the rails there long enough to make it worth going and deleting a piece. So I'm just going to say I'm naming this y, which is therefore u to the negative 10, because u is x squared plus 2. So dy dx is dy du du dx. dy du is negative 10u to the negative 10 minus 1, so minus 11. And then du dx is 2x. So this equals minus 20x times u to the negative 11. So x squared plus 2 to the negative 11. Okay, this one has a product. So u equals x cubed plus 2. V equals x squared minus 1 squared. U prime is 3x, drop a degree. V prime is, differentiate the candy to the 1, differentiate the chocolate, 2x. That's the derivative of x squared minus 1. So u prime v plus v prime u is 3x squared times x squared minus 1 squared plus 4x x squared minus 1 times x cubed plus 2 equals, I'm again going to factor out the lowest power of x squared minus 1. So here I'm left with 3x squared times x squared minus 1. And over here I'm left with 4x x cubed plus 2. So 3x to the fourth minus 3x squared plus 4x to the fourth plus 8x. And you could factor this totally, and you could factor an x out of that if you wanted to. So this time we have the quotient rule. U equals x squared plus 4x. B equals, so U prime equals 2x plus 4. B prime equals 2, whatever's in the parentheses, the chocolate, times the derivative of the chocolate. So U prime V minus V prime U over V squared. 2x plus 4, 3x cubed plus 2 squared minus, 18x squared, that's from the 9x squared and the 2, times 3x cubed plus 2 times x squared plus 4x all over 3x cubed plus 2 squared squared. Okay? So I'm going to factor out 3x cubed plus 2. So that leaves me 2x plus 4 times 3x cubed plus 2 minus 18x squared x squared plus 4x over 3x squared plus 2 to the fourth. Hope to be able to continue to read that. So I have a 3x squared plus 2, 3x cubed plus 2 in the top. And then I have 4 of them in the bottom. So I can, oops, I can't scratch that. I can cancel that with one of these. So that I have this piece. I'll write this. Okay, so now I'm going to put these together. So I've got 2x times 3x cubed plus 4x plus 12x cubed plus 8 minus 18x to the fourth minus 72x cubed. I lost a 3 somehow. Okay, so negative 12x to the fourth minus 60x cubed plus 4x plus 8. Could take a 4 out everywhere. So there's that. Okay, so this first one, I want to find where the tangent line is horizontal. And horizontal means the slope is 0. So I want to find where the tangent line has slope 0, which means where the derivative is 0. So I'm going to first rewrite this like that. So then the derivative is 1/2 times the chocolate to the negative 1/2 times the derivative of the chocolate. Now be careful, because when you see this, you're going to want to say that it's 0 plus and minus 3, but that negative 1/2 means that's on the denominator. So when that's 0, this is undefined. So let's be careful and write this. 1/2 times negative 2x is negative x. This is on the denominator. That 1/2 makes a root. The negative puts it in the bottom. So if I set this equal to 0, then that means negative x is equal to 0 times root 9 minus x squared, which for all x, where this is defined, is 0. So x is 0, and that's the only solution. Again, plus and minus 3 make the derivative undefined. That's not a horizontal tangent. Okay? And here we want to find the equation of the tangent line to the graph at this point. So the first thing we need is the derivative. So 2/3 x cubed plus 7 to the negative 1/3, because 2/3 minus 1 is negative 1/3, and then times the derivative of the chocolate, the inner function. 2/3 times 3x squared is 2x squared. I didn't actually have to write it this way, but anyway, so f prime of 1 is 2 times 1 squared over cube root 1 cubed plus 7 equals 2 over cube root of 8 is 2, so 1. F of 1 is 1 cubed plus 7 to the 2/3, so 8 to the 2/3, which is the cube root of 8 squared. So we would have y minus the y value that we know equals the slope times x minus the x value that we know. So y minus 4 equals x minus 1, and if you want it in slope-intercept form, you just add that 4. Okay.